This video will cover intermolecular forces. So intermolecular forces, abbreviated just IMFs, are forces of attraction between molecules. And with intermolecular forces, an understanding of them is critical for understanding solutions and solubility. So if you don't fully understand intermolecular forces and are able to identify them, right? If you're able to identify what intermolecular forces a compound has, you're going to do a good job of understanding the solubility of it and the reactivity of it, right? So that's why it's critical to get a good understanding of these. Now there are four major types of intermolecular forces. So number one is dispersion forces. So all molecules have dispersion forces. And these dispersion forces increase, so they're stronger, with greater molecular weight and polarizability. All right, so before I go on, I want to kind of define what polarizability is. So imagine we have two atoms, atom A and atom B. Atom A has an electron cloud that's that big. Atom B has one that big. So you got electrons in the electron cloud here, the different orbitals, subshells, etc. Right? This electron cloud is not always 100% perfectly spherical, right? It can move, right? The electrons move around, so sometimes it may shift and it looks more like that. Or it could shift to the right and look more like that, right? Just instantaneously it might do that. What dispersion forces are interactions between the instantaneous dipoles in electron clouds. The larger an atom is, the larger its electron cloud, meaning it has, one, a greater chance of just these instantaneous dipoles, and two, the instantaneous dipoles would be greater in magnitude. You would have more electrons than you have in, atom A. Atom A might have an instantaneous dipole that looks like that, but there's just not as many electrons. So when you're trying to increase polarity or polarizability, right, it increases with greater molecular weight and then also, right, more electron shells, but those kind of go in hand with each other. So I want to go through a list of a few compounds. So, we got your compound here, and then boiling point. And boiling point is a trait that indicates how strong intermolecular forces are. Because if the intermolecular forces aren't very strong, it's not going to be that difficult to break up interactions between them and make it so they go into the gas state. But if you have stronger intermolecular forces, then it requires more energy to break up those interactions and make the atoms go into the gas state, or the compounds go into the gas state. So I'm going to list the halogens here: F2, Cl2, Br2, and I2. So these are all halogens. They're in the same exact column on the periodic table. So the only difference between them is you're getting bigger each time. The boiling point of fluorine is 85 Kelvin. The boiling point of chlorine is 239 Kelvin. Bromine, 332 Kelvin. And iodide, 458 Kelvin. Right, at room temperature, fluorine's a gas, chlorine's a gas, bromine's a liquid, iodine is a solid. So all you're doing is increasing the molecular weight, but more importantly, since these are just diatomic, right, each of these is just a diatomic compound, you're increasing the polarizability. And that polarizability is making the intermolecular forces of attraction stronger for the compounds that are more polarizable, that have a greater molecular weight. So I'm going to do one more list here. And this time it's going to be more about just increasing the molecular weight of a compound. So these are going to be all hydrocarbons here. So methane, and then we've got propane, hexane, and octane. Boiling point of methane is negative 164 degrees Celsius. Propane, negative 42. Hexane, 68. And octane, 126. So again, at room temperature, we got a gas, a liquid, and a liquid. All we're doing here is increasing the molecular weight of the compound. But what that is doing is we have more dispersion forces the greater number of atoms you have in a compound. And that's increasing the boiling point. So that's dispersion forces. Number 2 is going to be dipole-dipole interactions. And recall that a dipole is when you have a difference in electronegativity between two atoms. So, an example, if you have an OH bond, oxygen is much more electronegative than hydrogen is, so it pulls electron density towards the oxygen. So the oxygen is more electronegative and has more electron density, and the hydrogen is more electropositive and has less electron density. Now this is a special type of dipole-dipole interaction that I'll talk about next. But all dipole-dipole is it's between two polar compounds. So an example here is acetonitrile. Right, the dipole is towards the nitrogen. So what happens now is in solution you have more negatively charged nitrogen, a more positively charged carbon, and they can have dipole-dipole interactions. Now the most common dipole-dipole interaction you'll see is the third type of intermolecular force, and that's hydrogen bonding. So this is a dipole-dipole interaction between a hydrogen bonded to oxygen, nitrogen, or fluorine, right, an electronegative atom, and oxygen, nitrogen, or fluorine. So an example, most common classic thing you could think of would be water. So what happens is the negatively charged, I'm going to make these more dashes so they don't look like electrons. But you have the more negatively charged oxygen coordinates to the positively charged hydrogens. And you get this a kind of network of these hydrogen bonds. You could also have this between, ethanol. Anything that has a hydrogen that's bonded to either an oxygen, a nitrogen, or a fluorine, and then an oxygen, nitrogen, or fluorine. This is why water has such a high boiling point for a compound with a molecular weight that's pretty small, right? Water, molecular weight is 18 grams per mole, and the boiling point is 100 degrees Celsius. Methane has a molecular weight of 16 grams per mole, so virtually identical, and its boiling point is negative 164. That's a massive difference, and it's because of these very strong intermolecular forces of attraction with the hydrogen bonding. This is also why generally polar compounds, which are compounds with a dipole, are going to be soluble with water because the hydrogen bonding and the dipole-dipole interactions between your polar compound and water. So like ethanol and water. I mean, that's beer, right? Ethanol and water. And there's not different layers of ethanol and water. It's all mixed together. It's soluble together because of the hydrogen bonding. So nonpolar compounds are going to be soluble in each other because of the dispersion forces. So when you get gasoline, that's not just one type of hydrocarbon. There's a bunch of hydrocarbons in there. But you don't notice different layers because they're all soluble within each other. Last one, number 4, is going to be an ion dipole. Right, so think here like a salt dissolving in water. So I got sodium plus. That coordinates with the electronegative oxygen. And then you have your negative chlorine that coordinates with the hydrogens. So this would be ion dipole. And again, critical for what dissolves in water. Salt dissolves in water. Other types of metals will dissolve in water. So less common salts, right? Calcium chloride or sodium bromide. Salts you don't necessarily think of. Now you're more used to probably like sodium chloride, but all of these dissolve in water because of the ion dipole interactions. And the order I gave them in, so starting with dispersion, then dipole-dipole, then hydrogen bonding, and then ion dipole, that's the order of their strength, increasing strength. So dispersion forces are the weakest, and ion dipole forces are the strongest.